part of the second half of chapter 17, which has the solubility in it. This will start exam 4B. So, first off, we're going to start with the definitions. First thing is solubility product. Okay? It's the dissolving and forming of solids from solutions. Way back in chapter 12:11, we did precipitates. Well, we're back, except now we're going to do the math. So, solubility product is the product of the solubilities, which is a big way of saying how much will dissolve. Abilities, can't spell, of the dissolved species. Now, this is still an equilibrium. So two things apply. We have a K value, more about that in just a second, and our concentration will be in molarity. Our solubility product is a K, and it's Ksp. We talked about Ksp before, but now we're going to apply it. And so it is the equilibrium constant that is basically the product of the concentration of the ions in solution. And we're going to work a few in just a minute, but before that we will walk through the definition. Okay, so these are the definitions. It's the equilibrium associated with precipitate formation. So here we go, an insoluble compound. This one is silver chromate that forms. It is a solid that forms, and the solid is the insoluble compound. It results from two soluble solutions. Okay? So the solubility product constant basically comes from our equation. And what you're going to do is you're going to product raised to the coefficients, and here you're going to have the coefficients based upon the number of ions you have. Now, if you'll remember, the rule of thumb is pure substances, in this case solids, have an activity equal to 1. Therefore, in the K, the value goes to 1. So if you'll notice, we start with our K here. This is a solid, basically, so it's 1. So when it drops out, here's your Ksp expression. This is the generic. And notice that the X values and the Y values are based on the charge. So it's critical that you know the charge of the species that you're dealing with. So for example, for silver sulfate, it's going to dissociate into 2 silver ions but only 1 sulfate ion. So when you get the Ksp, remember the solid is dropped out to 1, you have Ag squared times SO2, 2 minus. Now notice our coefficients are 2 and 1 here. So the next one, we're asked to draw the Ksp expressions for each of these slightly soluble salts. That means they'll have a K associated with them. So for example, if you write out the entire equation here, it's going to be copper plus bromide minus. You have to remember the charges, and remember, go back to the periodic table. So copper can be 1 plus or 2 plus, and in this case, it's 1 to 1 with bromide. So if bromide's 1 minus, which is his only option, and copper has to be 1 plus. So your Ksp expression is equal to the copper plus times the bromide minus divided by copper bromide. And remember, this is your solid, so it drops out. So your Ksp expression ends up with the copper plus 1 times the bromide minus 1. So that's the expression now. Now you can make your life a little bit easier by going ahead and dropping it out. So again, on this one, we're going to dissociate. So you're going to have mercury 2 plus 2 iodides 1 minus. Remember, this is your solid, so it drops out. So your Ksp here is the mercury concentration times the iodide concentration squared. Now notice that this 2 strictly goes as the exponent. You do not have a 2 within the box. Okay, so these two are relatively simple. So we'll move on to one that's a little more complicated. Again, this is going to be your solid. This is going to dissociate into cobalt. Now, arsenate is 2 minus. So the cobalt here has to be 3 plus. And it's aqueous. And then you have 2 of the arsenate 2 minus ions. So your Ksp here is equal to the cobalt 3 plus cubed times the arsenate. I think I just reversed that. Think about it. If the cobalt is 2 minus, there are 4 of them. Yeah, so it's got to be 3 minus. And so that makes the cobalt here 2 plus. Okay, so it's 2 plus to the 3, OS4, 3 minus squared. Okay, so you've got to watch the charges and you've got to pay attention. Some of them are not that common, like the arsenate ion. It's under phosphorus, so it's 3 minus. I forgot about that one. But this is simply what it is. Just remember that the solid will always drop out. So when we do these problems, we're going to get into much higher numbers. We won't necessarily have the quadratic, but we may have to solve for x to the 3rd, 4th, 5th, etc. More about that in a minute. So this one's pretty much done.